So, ladies and gentlemen, whoops, it works fine. We have DAX today. In principle, it's just the inverse of an ADC, but we go from this time from digital code to analog signals, and let's see how this can be done. Let's have a very short look at definitions. They are more or less the same as what we have seen last time, but then let's have a look at principles, and you will see that a lot has to do with matching, meaning that after you have gone through resistive, capacitive current steering, especially the current steering ones, which are used a lot, we have to talk about matching a little bit, because we work hard to really match currents, capacitances, and so on. And then let's have a look at some realizations, not only 10-bit, 12-bit, 14-bit, and at the very end, some low power ones, and I have a figure of merit for you to compare all those DACs. First, something about definitions, but definitions are very similar as before. When we have a digital code, the digital code will determine what fractions of the reference are going to be switched together. For example, if you have 1, 1 and the rest is O, then we have, of course, 1/2 and 1/4 of the reference put together towards an analog signal. And after that, because the clock is still in there, we have to do some filtering, of course. So actually, a D to A converter is going to convert a code, represented by B's here, into, depending on the reference voltage, which could be 1 volt or something, towards an output voltage. And the number of bits determines what the resolution is, 8-bit, 10-bit. The smallest one, the biggest one, is the most significant bit, and the other one on the other extreme, where we have for 10 1,000, for example, this is the least significant bit. And we put them all together. Again, we have quantization noise in the sense that the difference between the quantized analog signal and the actual analog signal gives rise to a stepped waveform looking like this. And as a result, when we take the RMS value, what we have done already, the RMS value of this, the RMS value, we get the maximum squared divided by 12. And as a result, you can derive a signal to noise ratio. This is the signal voltage peak to peak. This is the signal power. This is the noise power, and the signal to noise ratio simply depends on how many bits I take. And you know this expression. In dBs, it's even better known that we take 6 times the number of bits, and we add a bit, and that's it. And there are two very important characteristics characterizing as well A to D converters and D to A converters. The first one is the differential nonlinearity, which is the biggest step minus the LSB. So when we take a LSB, which is the right one, which is a bit smaller than this, what is excessive to that is the differential nonlinearity. It is the biggest step in the whole conversion, AD or DA. Whereas the biggest deviation from the average is the integral nonlinearity. I will talk about that a lot when we talk about how to divide in a segmented DAC, for example, how to divide over a binary and a unary portion. So those specs will come in heavily. And of course, from the analog point of view, there is still offset and difference in slope. Another one, which is more important now, which is coming in very strongly in DACs, is the glitch energy. Glitch energy, what does that mean? A glitch means that there is a sudden increase in energy before you reach the average value. This is a 3-bit conversion. We see that indeed when you go from digital code to an analog signal, the transitions are not always that clean. This is a glitch. And of course, this energy should be smaller than the least significant bit. Where is that coming from? Well, if you switch, for example, a 1110 to a 0001, you have an enormous change in current, first composed of many small currents and then one big current. As a result of mismatch, the sum of the smaller currents can be larger than the large current. And as a result, you have a glitch, an overshoot, and then it's settling towards the final value. That's an additional spec, especially for dynamic performance in DACs. And we can do some calculation. I'm not going to do too much of that. For example, if you have this current which is switched off, I would expect, if you put that current over there, you would expect this kind of output waveform here. When the second one comes a bit too early, or this one comes a bit too late, we have a glitch in between, and that glitch energy should be less than the least significant bit. It's for the camera. So we have to watch that for dynamic performance. and I'll show you which ones are better than some other ones. Another one, of course, if I get my analog back, a very important spec is going to be how much are the harmonics. We see here the fundamental followed by a number of spikes, whatever combination you can get, harmonics or intermodulation, and the total sum and power of all this with respect to that is a spurious-free dynamic range. And finally, where ideally you can get a very high resolution, you always lose a bit when you realize an A to D or a DDA converter. And at the end, of course, for large signals, there is always distortion. For large signals, there is always distortion. Remember what I've said some time ago about distortion. It always pops up at the large input signal levels. I'm on there now. Okay. So let's have a look at the principles. How can you do all this, going from code to an analog signal? Let's start with the resistive ones, capacitive current steering, and then let's talk a bit about matching, how to do things, before we go dive into all kinds of realizations. Simplest one is probably this one here, where I have a bunch of resistances and a bunch of switches, and the switches are driven by the digital word. We have here, this is the first bit, second, the third, and the fourth for a 4-bit digital code. When this one is closed, there is nothing going through, but for example, if you have 0010, then clearly this switch is going to be closed, and that voltage is going to go through simply a buffer to the output. Nobody does it like that, because if you would do this, that means that you have a whole bunch of switches here and a whole bunch of resistances. So that, and also adding voltages with the voltage buffer, that's not an easy thing to do. Also resistances, we need too many resistances, because this is not just a digital code. We have to close many, many switches depending on the digital word. So a way out is to use binary resistances, because if we now switch that reference in, depending on the digital word, which is on the right hand, the first one and going to the left, you see the switches are going to determine whether I switch to the left or the right. If they are switched to the right, they are all connected to ground, and then there's nothing at the input here. But if one of them is connected, for example, I take again a 0, 0, 1, 0, why not? Then clearly this one here is connected, as shown here. And that means that indeed that the reference voltage is going to be, that the reference voltage has a 4 resistance and a single resistance over there. So a fraction of the reference voltage as a result of the size of the resistance, a fraction of the reference voltage is going to be appearing at the output here. In order to do that, we need matching between this resistor and that one, and that one, and that one, and that one. And clearly, if you go to 10-bit, for example, we have a matching between a resistance which is 1,000 times larger to a resistance which is smaller. So to match two entities which are so widely different is very difficult to do. So this is why, rather than to try to match a larger resistance to a smaller one, there is an easy trick. We can take all resistances equal. But before I show that, let me show you that indeed here we have a chance of a glitch, because if I switch, for example, those 3 out before I switch that one in, which is a larger one, maybe the sum of those 3 voltages here is larger than this one here. And then, of course, in the transition from the 0001 to 1, from 1110 to 0001, I have a glitch. To match the resistances, this is a solution. It's an R2R network, used heavily a long time ago when ion implantation was introduced. Then all of a sudden we could match the resistances. Match to how much? 8, 9-bit. I'll show you why. So for 8, 9-bit, yes, I can do this, because now all the resistances are more or less equal. This is 2 resistances in series, 2 in series compared to this one, or we have 2 times the resistance in parallel compared to this one. But all the resistances have more or less equal size, and they are easier to match. Okay? And that means that indeed, by switching out switching in or out those switches here, I can send parts of this reference towards the output here. Let's see how this works. This is a little bit more tricky, but not that difficult to see. I try to sketch all the currents when all the switches are on. And there you see that indeed, when the switches are on, the resistance seen on the right here is going to be, this is 0, this is 2R, and this is switched in, or if it's out, it goes to ground, but if it's switched in, it goes to a virtual ground, which is also 0. So when you look at the resistance here on the right, I see a resistance R, because this is 2R in parallel with 2R. And 2R in parallel with 2R is R. That means that I see one resistance R. That means that over there I see a resistance 2R, because R plus R is 2R. So that means that I see 2R in parallel with 2R. Here I see a resistance R again. Here I see a resistance 2R in parallel with 2R. I see here again R plus R. I see 2R in parallel with 2R, so I see a resistance R. That means that the current flowing is going to be the reference divided by that R. And actually this is a reference current IR. But because of the division at each node, I have a current IR, there IR over 2. Let me take, I have IR here, IR over 2, IR over 4, IR over 8. This is only for 4-bit. I can go to 10-bit with it, 8-bit, 10-bit. But each time the current is divided by 2. And now, if I switch in some of those currents, that current here that flows either to ground or to the input is IR over 8, over 4, over 2, and this is the current itself. So depending on the digital code here, I'm going to have a summations of those currents and fractions of that current. So if I sum all the currents, I'm going to have a current which is all the currents, and I have the maximum output voltage here. So depending on which switches are closed, I'm going to have a sum of currents which are binary scaled. That's it. And then I need a filter to get rid of the clock frequency, and that's it. Now what's the problem with this? Well, the problem with this is, of course, how well can you match resistances? Everybody says it's much easier to match capacitances. So maybe we should, rather than to do this with resistances, can't we do that with capacitances? Yeah, here we go, capacitances. Used a lot. I'll show you in just a moment that you can easily match capacitances to 12-bit with the same effort as you can match a resistance to 9-bit, 9, 10-bit. So that means that with capacitances, we will have to have capacitances binary scaled again. Here we go. This is a very simple example, of course. Only 3-bit capacitance, double capacitance, 4 capacitance. For a 10-bit, that would be then we have 8 times and then 16 times and so on and so on. How to do all this, I'll show you, but assume that we can do that. And we have clocks, of course. It's like a switch cap filter. You always need clocks. And in those clocks, what are we going to do? Well, this is the first clock. And this is going to be the second clock. Let's see what happens. First of all, for clock 1. Well, in clock 1, the reference is simply charged on all the capacitances. Again, you see that this is closed. This works as an amplifier. This is a virtual ground, meaning that all the capacitors are charged to the reference voltage. This is simply open. You see, this is open, this is closed. And now all of them are charged to the reference voltage in the first phase, and in the second phase, depending on which switches are closed, some of them are going to be discharged over this capacitance to the output. So again, we have like a larger resistor, or depending on which switches are closed, the capacitances for which the switch are closed are going to be discharged and transfer their charge towards the output, and the charges are binary scaled. We have a large charge, half, a fourth, an 8, a 16, and so on and so on. Why is that better? Simply because it's easier to match capacitances. That's all. And you have a clock. You may not like that. With the resistances, there is no clock. You may prefer that, but we have learned to use clocks, so what's the problem? We need a filter after that anyway to filter out the clock, so this works fine. Of course, some capacitances are no good. We never use junction capacitance, of course. Metal to metal, poly to poly before. That's what's being used. Now, the third category is current steering. Why using all this? Why don't you simply use a current source here with a value 20 microamp, double, and double again, and double again, 10-bit, for example. And now, depending on the switches, you're going to sum the currents for which the switches are to the right. And that's going to give an output voltage, which is the output resistor times all those currents. That's it. Current steering DACs are used most of the time. Why is that? Is it because it's easier to match currents? No, because it's easier to make high speed. Because you see that now we have a current source sitting there, simply driving a current into, yes, that's going to be 50 ohm later on. Well, driving a current in a 50 ohm is a much wider band system than switching capacitances, as you have just seen before, or having all those resistances with an operational amplifier. There is no operational amplifier in there, and an operational amplifier always means that it's going to be a bit slower. So this is much faster for whoever is interested in high speed. You're going to use current steering DACs. And as you know, in the figure of merit at the end, there is always speed. So the higher the speed, the better you're off. And indeed, 10, 12 bit nowadays, and even more if you do calibration, can be done up to, I'll show you, 1 gigasample per second, 4 gigasamples per second, using this technique. Okay? But now we have to match current sources, and matching current sources is actually matching transistor sizes, because transistor size corresponds to current. So we have to talk about matching when you look at this. And of course, we still have that problem with the glitches here, because indeed, if I switch from, and this is a very simple example, I thought I have a little, yes, a better one here, where I go a little bit more current, half current, 1/4 of the current, 1/8 of the current. If I switch, for example, all those in, I get 1/2 plus 1/4 plus 1/8. That's close to 1, isn't it? If I switch them out to switch that one in, and for mismatch those are higher than this one, then I get a glitch, because the sum of those fractions is supposed to be smaller than 1. So that shows that indeed it's easy to get a switch. This is an example where the current is converted into voltage by means of an operational amplifier. The high speed one simply uses the resistance, of course. Now we have to talk about matching. How far can you go? What can you do about it? So that's why I have injected a little bit about matching before we go to all the considerations about binary and unary DACs. Because all this is because we try to improve matching. So let me talk a little bit about matching now. Matching has to do, well, we have two different kinds of matching, random and systematic errors, which cause mismatch. Mismatch is also expressed by another spec, which is called mode rejection ratio, but that's for op-amps. I would like to talk especially about this. What can you do about it? Okay. And there are many texts on this. Nobody gives you the whole story because many companies don't even know how well their things are matched. They just take some average values. Matching is simply a result of when you take a large number of transistors, 10,000. So you need somebody to do measurements automatically, I hope for you. And you look at the VT, for example, an important MOS parameter. You see that there is going to be an average VT and there is a spreading around it. Spreading meaning that indeed this is Gaussian. It should be Gaussian, otherwise there is a technological problem. And Gaussian means that indeed there is a sigma, and within plus minus 3 sigma we have like 99.5% of all the devices. That's what sigma means, isn't it? So that spreading here, that's what we are talking about, because if I make 10,000 devices or 1,000 devices, they all have a different VT. Meaning that indeed that spreading is inversely proportional to the area of the transistor. I will call this area, whereas I reserve this for size. This is size, and this is area. Size means W over L, sizing most devices. That's where it's coming from. And this is area. This is W times L. Now, the larger I make my devices, the smaller the spreading is going to be. It's that simple. I can make them huge, like power devices, very well matched. And that parameter here has some technological parameters in there, because actually it is the oxide thickness, because this has to do with charges in the oxide, which are redistributed in a different way. Meaning that once in a while the charge is a bit closer to the top and a little bit deeper and a little bit closer and so on. And the other thing is doping level. This represents the technology, changing all the time. But this is the oxide thickness. Meaning that indeed, when I take the oxide thinner, then the AVT gets smaller and then the spreading is smaller. So going to more advanced technologies helps. It's not worse for matching. No, it's better. It used to be better, because the AVT goes down with the ox, and it goes down in a very reproducible way. I'll give you some numbers in just a second. It goes down in a reproducible way, and because most of our technologies are based on NWEL, that means that the PMOS device is worse off, which is the opposite compared to one of ref noise. So where is that AVT coming from? Well, you have to do measurements, that's all I can say. And when you look at technologies, TSMC included, UMC, and then Charter, and so on, and before so many different ST, for example, and you look at channel length is for standard technologies about 50 times larger than the oxide thickness. 50 times. Not for high voltage, of course, standard CMOS technologies. So that means that for a half micron CMOS technology, you would have an oxide thickness of about 10 nanometer. And actually that AVT is also about 10. Because when you look at those values, you see that indeed we have some technologies there which give you something like 10 watt. This 10 is actually 10. This is millivolt micron. So we have, this is going to be 10 millivolt micron. Meaning that if I make a 1 by micron transistor, I can expect a sigma of about 10 millivolt and the plus minus 3 sigma of 60 millivolt, which is enormous, of course. And it's getting better because for a tin oxide it gets better all the time. Up till here, all of a sudden there is a big problem. Down 0.13, there's a big problem. All of a sudden it doesn't go down anymore. Other things have come in, like gate depletion because it's poly. One reason why people go back to metal gates. Gate depletion is one. Line edge roughness and some more things. Lots of papers, lots of talking. But there are very few companies guaranteeing less than 2.5, let's say 2.5 millivolt micron. And that's the problem. People working in, what was this, 90 nanometer and 65 nanometer. And maybe at some point I should make one to 45 nanometer, which is here somewhere, isn't it? People expected something like this in terms of matching, and they only get that. And that's why all of a sudden all those digital people start screaming about mismatch. They can't make a big chip anymore with the matching they expected. It's only here, and they expected that. So yes, matching is a problem now. If you work in 65, 45, and so on, you only get numbers like this rather than that. And as a result, you have a larger than expected value and a larger than expected mismatch. There are some other parameters that play a role too. It's not just VT, isn't it? You do remember the expression of the current? Expression of the current I have somewhere. Here it is. Very simple one. I know it can be much more complicated. But when you talk about mismatch, everybody still takes the most simple expression. Mismatch in all those other parameters is not yet known. Everybody talks about the VT or mismatch on the K prime or the W over L here, for example. So we have indeed a AVT and a AWL and a AK prime and so on and so on. And there is only one other one that's important. That's this one here, because that's a bigger one. This one is fairly small because on the K prime this is smaller compared to this one. This is a well-known one. It seems to have to do with photolithography. Big machines getting bigger and more expensive all the time, but trying to reproduce accurate W over Ls is a difficulty. And actually the value in there doesn't seem to go down with technology. It's a little bit smaller today than 2% micron. This is 2% micron, okay? And it's worse for PMOS again. And it's a little bit less, 0.015, 1.5%, 1.8%, values like that, but still about 2%. That's why some people say, well, at some point, if the AVT gets very small, this is a more important one. Maybe. So the AVT is important for VT and the WL one. And this one is also negligible because in your differential pair, for example, you always connect the bulb to the source, and then the body effect is gone. Okay. Now, where do they play a role? Well, there are two simple circuits with two equal devices. It's either a differential pair or it is a current mirror, isn't it? And current mirrors, yes, we are going to make current mirrors for our current steering DAC, isn't it? But let's first say something about the differential pair. It's very simple. If I look at the voltage I need to make the output voltages equal, then clearly a mismatch in the resistance or a mismatch in K prime or W over L or VT is going to come in. And it's fairly easy to calculate what the contributions are. if there is a difference in VT, for example, simply compensating that is going to be sufficient. If there is a difference in VT, simply compensating that is going to give you the offset, sure. But the other ones are all working on the current. That means that in order to refer a sigma or delta K prime to the input voltage, I have to go through the transconductance of the transistor. So that's why all the other ones algebraically added, plus minus, plus minus, plus minus, have to go through GM over I, and that's why the VGS minus VT is in there. Leading to the obvious conclusion that if I make that small, and the smallest is weak inversion, of course, if I make that small, then clearly I only have to struggle with the spreading in VT, and that's why so many people keep on talking about the AVT, because that's the one we can't get rid of. There are still some attempts to cancel by means of trimming with a resistor, trimming the resistor, trying to cancel the delta VT, but that's difficult because we have to make sure about the biasing point first. So a single trim is impossible. We have to trim this first and then trim this to get rid of this in order to have 0 over there. So that's hard to do. Okay. Now that's for the differential pair, that's offset. And of course that's one that's even more interesting for us. It's the current mirror, because the current mirror says that if I make a whole bunch of currents, and the currents are all scaled towards the sizes of the transistors, how is the matching going to be of all those currents? And clearly, now, well, first of all, it's the transistor size that's come in. The transistor size comes in. The 2% micron, remember, in this. And now, if I have a delta VT, it's the delta VT now, which is going to be multiplied by GM towards the current. And it's now the delta VT, which is scaled on the VGS minus VT, leading to the well-known conclusion that I have to take large VGS minus VTs here to kill this contribution. And then I only have to think about current matching in terms of size matching. And indeed, that's one of the big problems in DACs, of course, because making a large VGS minus VT means that the VGS is going to be large. And the VGS can be made large if I have a large supply voltage. But how do you do that on a small supply voltage? So actually, in that figure of merit, we should have the supply voltage in there. But nobody has done that yet. That's for you next time. So that means that indeed, it's easy to, on 3.3 volt, for example, the latest one on the last ISCCC a few weeks ago used 3.3 volt. Then it's easy to have a large VGS minus VT, of course. And with a large VGS minus VT, at least you don't have this problem. And then it's all a question of matching. And some other problems I'll show you. So that's matching of currents. Be careful. Matching currents is not that simple. Currents flow in the supply line. And if we talk about 10-bit, for example, 10-bit means that I have currents in a ratio of 1000, an easy number to remember, isn't it? From 10 microamp to 10 milliamp. 10 milliamp, if I have 10 milliamp flowing in the supply line, that's not that easy to do. Series resistances may give you more problems than the matching between the transistors. So there is always a concern that indeed ohmic resistances here giving you a systematic error are more harmful than the matching components here. So now in the drain of a transistor, in general, because we are going to use that, oh yes, saying again that the current of a transistor has all those components. And now if we don't talk about VT mismatch and we don't talk about the WL mismatch, we talk about the current itself, how is that linked to the delta K prime over K prime and linked to the delta VT? Well, it's like taking an RMS value. When I take the RMS value of the mismatches in the current, it's going to be the value of the delta K prime. The K prime is in there, as you remember, which includes mainly W over L. And this one here, and of course this one is scaled because I have a VGS minus VT in there. And for once, yes, I would like to write down that for weak inversion it's different as for a strong inversion. Actually what was in there was GM over I. And there are so many papers saying that, well, we shouldn't replace the GM over I, we have to keep the GM over I. I don't know. I prefer to replace that in weak inversion by NK2 over Q, and in strong inversion by V just minus Vt. But you're welcome to keep that as Gm over I. There is no need to write a paper on that, okay? Just keep it in there. And now we have a combination of those two. Both of them have the WL in there, remember? All those sigmas had area in there. And that's going to be an equation we are going to use later on to design a DAC, because we will get the area out of matching considerations. Okay? Whereas size will come out of the current equation. If, for example, your minimum current is 10 microamp, it's trivial for all of you for a certain chosen V just minus Vt and for a certain given K prime and N to figure out how the W over L must be. And from the required matching on the current, for example, 0.5%, then it's fairly easy to figure out how much the WL has to be. And from W over L and WL, we will figure out W and L separately. That's going to be designed. That's coming, and that's where it's coming from. Okay? Now there are some systematic errors. I shouldn't say too much about that, but we will struggle with that too, huh? Yes? The main problem of systematic error is the difference in VDS of a transistor. Amazing what we will do later on to make sure that the current is independent of a VDS of a transistor. Why is that so important? Well, I'll show you we need to make current sources, and the current is set by the VGS. But if the VDS is changing, we have a different current. Here it is. If I simply take a current mirror, then this VDS here, which is going to give you a slightly larger current, because transistors are never flat in their IDS-VDS characteristic. When the VDS goes up a little bit, the current goes up a little bit and gives you an error on the current which was set at a particular value. So, of course, we will put a cascode in there, etc., etc., etc. We'll talk about this. And the error is quite large, because if you do that for a simple current mirror, for example, the error here has simply to do with the slope. And the slope is described by the early voltage. Actually, the output resistor is nothing else. This is in the modeling. The output resistance here is nothing else than the VE. We put a voltage in there, which is in volt per micron channel length, times the channel length. This is a very simple model, divided by the current flowing in that transistor. Okay, this comes under modeling. And the larger the current, the smaller the resistor, the steeper that is going to be. Think about your 10 milliamps. And this is usually 4 or 5 volt per micron, and this comes then in micron. Okay? So this is the slope, and we have to do something about that, otherwise the currents are no more matched. And remember, you have to match the 10 milliamp down to 10 microamp. So it's very severe. That's a systematic error. It has nothing to do with deltas. It's simply there because of MOS modeling, MOS physics. And we can derive some other parameters from this. In a differential pair, for example, this is a bit more complicated, maybe, because this voltage is not necessarily the same, and because that impedance is very, very different from this one here. There is going to be a little bit of current seeping out of this. And this current divided by Gm gives an offset. And this is actually a result of a certain voltage here. And as a result, the ratio is a common mode rejection ratio. But this leaves us too far. We don't have to go that far. Let's skip this. And common mode rejection ratio, of course, is then always, and offset is always the result of a random contribution and a systematic contribution. And the smallest one wins. Now, the main thing in all this is, what can we do about it? But before I do that, before you try to make very low offset and high common mode rejection ratio by putting a larger resistor there, because this is the current. When I go up and down with my input voltage, this current is the culprit. This is the current here that is seeping out of there. So now do we have to make all those current sources with infinite output resistance? Well, we can do that at low frequencies. It's like asking an op-amp where they want high gain. At low frequencies, it's a question of gain tricks. At high frequencies, it's a question of gain bandwidth. So that means that if you are interested in a DAC with high dynamic performance, The only thing that matters here is not the output resistance, it's going to be the output capacitance. And yes, the question is going to be, how can I make a number of current sources with ratio 1, 2, 4, 8, 16, 32, and so on, which are increasingly larger? How can I make them with a small output capacitance? Because the output capacitance is going to kill the dynamic performance. And the answer is very simple. We will put a very, 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 very small cascode in there. 1 by 1 in 1 micron, half micron by half micron in half micron CMOS. The smallest possible device. Because the smallest possible device is going to give you the smallest possible capacitance. And then that frequency is going to go more to the right. That value will be larger. So for dynamic performance, it's going to be a question of making capacitance small. I know the output capacitance of a small transistor is very similar to the input capacitance, the CGS, the CDS. But I'm talking about modeling again, but talking about matching is about modeling, isn't it? Here we go. CDS is very much CGS. And yes, I thought I had used that very simple model for the input capacitance of a transistor with minimum channel length. It is at K times width. And K is about 2 femtofarad per micron. So that means that yes, we are going to put 2 femtofarad per micron. Meaning that indeed we are going to try to make a very, very small device over there with 1 micron width, half micron width. If this is only 1 micron, I get 2 femtofarads. This is a struggle for fractions of a femtofarad. Fractions of a femtofarad. I'll show you later. So this is important later on, to be able to make a current source with very small output capacitance. And now what are the tricks that we can use to match all those current sources and capacitances and possibly resistances if you still like the R2R network? And yes, why not using it with a limited number of bits? Well, first of all, of course, we can't match, for example, a GM or a 1 over GM to a resistor. They all have to be resistances and nothing else. Or all capacitances, all metal-to-metal capacitors of the same layers. Okay, that's obvious, isn't it? Simple. All to be on the same temperature. How obvious is that? The area that I take with all my transistors may not be that large, but if it's very large and your chip is heated because you have some power devices on one end, you have a temperature gradient. And if you have a temperature gradient, of course we will work hard to compensate for it. Show you how to do this. But if you have a temperature gradient, the ones which are a bit warmer, and there is a temperature gradient in this room, I thought, but it's getting better, huh? The ones that are warmer are going to have a different value, not for capacitances maybe. This is just the distance of a dielectric, the thickness of a dielectric. But in the resistances, this will play, and this will also play in the K prime and in transistors. So temperature, the isotherms, we have to watch. And I'll show you compensation schemes for gradual changes, gradients, like temperature and oxide thickness, and also for ones which are concentrated in circuits like stress on a chip, for example, isotherms which are concentrated also. So temperature may come in, especially when we talk about current sources. Size comes in too. The larger the better. I've shown you that. But how much does it play? Is it really worth making it really large? I remember a chip, 1 square centimeter, only capacitances, a full square centimeter, to go to 14-bit without trimming. Can be done. Are you going to take a full square centimeter of little capacitances? So let's have a look at how size comes in. And for resistances is different as for capacitances. Resistances maybe we will use to derive current sources from. A current of a transistor is very much like a resistance, because after all, a MOS transistor is a resistor, which is modulated by voltages, isn't it? And we see that there indeed, it's all a question of size, local errors, rounding errors, jagged edges and things like that, meaning that if you make them larger, it gets better. And an easy value, if you don't want to go, oops, this should be micron, huh? And this should be ohms. Yes, once in a while I have to convert all my letters. Please change that. Microns and ohms. I didn't see all of them. So if I take a value, for example, something like 10 micron, which is already large for the smaller dimension, I get something like 0.4%, 0.5% here. 0.5% is 1 over 200, and 200 is 46 dB, and 46 dB divided by 6 is about 48, divided by 6 is 8. So it's easy to make a 8-bit ladder with the resistances without going to excessive size. So this is why 8-bit, the DACs, for example, and also A to D converters are with resistances. And they go down. If you make them bigger, it's going to help. Yes. Very different from capacitance. Different slope, you see. It's flatter. It's more a combination of local errors and global errors. And global errors means that actually we have gradients in oxide thickness, thickness of the dielectric between two metal layers, and so on. So if you have a combination, that line is flatter. But the absolute values are better. If we take little squares of 10 micron by 10 micron, this micron, and this is the side of a square, and this is micron, not millimeter. 10 micron by 10 micron, we are here somewhere, or even a little bit better. For example, let's take this one here, 30 by 30 micron, which is not that big, 30 by 30 micron, okay? Now then we get about, before we had 0.5, and now it's 0.05, 10 times better. We had, what was it again, 200, now it's 2000, that corresponds to 66 dB, that's 11-bit. So that means that with capacitor arrays of a certain size, let's take this size here, it's fairly easy to get to 11, 12-bit matching, 11, 12-bit DACs, 11, 12-bit ADCs. And we can go further too, but it goes down very, very slowly. So we really have to have excessive sizes before you get to 14. That's why I took a full square centimeter. Okay. So with capacitances, they match better, but they improve less when you go to bigger sizes in general. So that's about size. Size does help always, but in a different way for resistances compared to capacitances. Distance, yes, much less than before. Wafers are that size, sorry, I exaggerate, at that size, and they get bigger all the time. They become more homogeneous. The processing becomes more homogeneous over a big wafer, so distance is not important anymore so much as before. Orientation is important. Orientation, what does that mean? Orientation means that indeed the K prime is different in this direction as in this direction. We're working with a crystal. That means that indeed conduction has a K prime saying how much current you have for a certain voltage difference, and the mobility has to do with crystallographic homogeneity. So it's different. The mobility is different in this direction compared to this direction. So for matching, transistors must be lined up so they use one direction only, not both of them. Area to perimeter ratio, that's also important. That has to do with gradients again. What does that mean, area to perimeter ratio? Area to perimeter ratio says that if I just stretch a transistor, for example, I take this one, and I'm going to stretch its width and make it 4 times larger or above 4 times. Of course, local errors, for example, rounding, which is easy to see here, but also the effect of contacts, is going to be here less important than, for example, over there. Over there. That means that rather than to stretch a width, we have to make 4 equal devices which are connected in parallel by means of metal, as in bipolar before. Okay. So just playing with widths doesn't help. I have to make equal devices, equal shape. And shape actually is the ratio of area to perimeter. So they must have the same shape, so that whatever happens to this, it's always the same. All devices have the same shape, and we just connect them in parallel. And of course, if I try to match that onto this one here, and that comes next, we're going to put that one in the middle here, right in the middle, so they have the same point of gravity, but that's next. Okay? So that means that if you take a large number of devices, they must have the same shape, and they must have the same point of gravity. Point of gravity comes later. Nothing easier to match than a round transistor, but nobody makes round transistors anymore. They look beautifully, but yeah. It's hard to draw on the workstation. Still used for charge detectors and other special applications. Centroid layout is all about point of gravity, yes? Point of gravity, meaning that indeed, what does that mean? That means that if we have an oxide thickness, or in bipolar a beta, or what else can go wrong? Under etching, what else? A gradient from one end of a wafer to the other end, then if this is the gradient, that means that the ones perpendicular on this, those are going to have the same parameter. They have the same parameter. But the parameter value for this one is going to be different from this one here. That means if I take one with a thicker oxide and a slightly lower VT, for example, in parallel with one with a larger oxide or a higher VT, if I take those opposite ones in parallel, I average out the parameter value. So all differential pairs in the past have been made with 4 transistors, and the opposite ones are put in parallel. The opposite ones are put in parallel. This has been done for 40 years. It's still done. Now we can expand that, of course. With transistors, we're going to have many, many transistors and connected them so that they have, for a certain oxide, for a certain gradient, you put the opposite ones in parallel. And you can also do that with capacitance, of course. Here we go. If you match this capacitance to this capacitance, those two are in parallel. So 2C versus C is matched well. If this one is a bit larger than the other one, which is smaller, this is the point of gravity. That means that the larger one and the smaller one are in parallel, and the thickness averages out towards this point. And the blue ones are in parallel, and the green ones are in parallel, and then the purple ones are in parallel, etc., etc. Of course, if you keep on doing that, it's not going to be so nicely structured. Once you get to the largest capacitance, then they are randomly distributed over a certain area. And then you have to keep track where they are to put in parallel, of course. So that means that centroid layout means that they all have the same point of gravity. And that's used both for capacitances as for current sources, of course. And the dummies don't work either, because if you look at this, the ones on the side, of course, all those capacitances feel happy in terms of technological treatment, because they have capacitors in all directions, except the ones at the end. If this is the edge of my chip here, or of my capacitive area, this one, for example, is not going to feel so happy because there is no more capacitance over there, only there and there and there. So that means that the last one is always slightly different. So what can we do about that? The same technology we have to apply to a dummy ring all around that. For example, a dummy ring, which is the same as a capacitance, in order to fool this capacitance, to give the impression that there is not a capacitance here. So this one is okay. So dummy rings are used. I've never seen a paper to prove that, but I've heard many people say without a ring it didn't work. For example, if you have an array like this, the first one and the last ones are not used because there is the different kind of technology over there. Technology could be anything, under etching, metal layers, whatever. We can expand that when you listen to people like Tuinhout, Hans Tuinhout of NXP, for example. He could give you a whole presentation just talking about the end effects and putting layers on top. Very few companies publish what they do in that direction. NXP does. And another nice example is this one here, where I see a dummy ring indeed, and a nice example I picked from Eric Vito's, where you see indeed 9 capacitances, and they're all perfectly equal. You see the capacitance area here? And you see those little connection points, which, if they are aligned, they make a contact, and if they are not aligned, then we still have the parasitic capacitance associated with it, but not the connection. So they all have exactly the same capacitance because they have the same notches here. Okay. So they all have the same parasitic capacitances. And indeed, in order to make a ratio, you see that the connection here is such that we have a ratio of 7/2, and the 2 ones are in the middle, of course, to have the same centroid layout, to have the same point of gravity, and there is a dummy ring all around it. Dummy ring saying that indeed for the poor fellow in the corner here, Well, there is no more capacitance here. That means that this capacitor may be slightly different because of the technology. Well, in order to restore that, there is a dummy ring. I would make it even larger than this, wider, or put the same array of capacitance all around it. It takes area, but mismatch is area. You always need larger area for better matching. So whether you use a dummy ring or one dummy ring or two dummy rings is up to you, but this is one of the requirements to have good matching. And finally, just as a note on the side, bipolar is better, always better for matching. Why is that? I just want to mention that without going too much into depth in here. Simply because you remember the MOS transistor, the biggest problem of the MOS transistor is that AVT hidden in there, giving you a VT mismatch. And the beauty about a bipolar transistor is there is no VT. It looks like there is a VT. When you look at the current, when you look at the IV characteristic of a bipolar transistor, it's an exponential. It looks like there is an AVT there, even more than with the real MOS transistor. MOS transistor is flatter. Okay? It looks like this has a VT there, but there is no VT. It's an exponential on the current IS. And as a result, we don't have that. Also, the scaling factor of all those other parameters working on the current, which is the output resistor and the K prime and the W over L, okay? They also appear here, but now we don't have that many. They're all into that IS, and there are several contributions in there, sure. But the scaling factor, unless you go into weak inversion, is smaller. See, it's KT over Q, which is only 26 millivolt. If you take MOS devices in weak inversion, you have N KT over Q rather than this. So that's another reason why normally, and for high speed, this is large. I've just tried to convince you to make this large in order to matching of current mirrors. And then if this is large, you get all that. Well, in bipolar, it's always the same. It's never large. And finally, if you look at the temperature difference, we see that when this, for different temperatures, simply goes to T, that means that the temperature drift in bipolar goes with the offset in absolute value. If you would trim that to a small value, the drift goes down too. Not in MOS, because if you trim that to a small value here, I don't know what you have done, but this is always going to come in there. Okay. So those are all advantages. The main disadvantage of bipolar, it has a base current. But now this goes too far. I've said enough about matching. It's time we go back to DACs. Now we know how to make two transistors equal. It's going to cost you area. Okay? And we can do that with capacitances, yes, but we are going to try that with transistors because we would like to make a current DAC. Here we go. So the very first one, let's have a look. Well, here we go. We can make a unary DAC or a binary DAC. What does it mean, unary? Unary means that we take a whole bunch of equal current sources. For example, for 10-bit, we need 1024. We need 1000 equal current sources. And for the least significant bit, we take 1. And for the next one, we take 2 in parallel. And for the next one, we take 4 in parallel. And we take 8 in parallel, and so on and so on. And at the end, you take them all in parallel. Okay? And they are better be matched, so we have to make a selection from this. This is a unary current steering DAC. Now, of course, we need 1024 current sources. Wouldn't it be easy to take current sources in a binary way? We take only 10 current sources instead of 1000. And the 10 current sources, here we go, binary means that we have a current source with a value 10 microamp, for example, 10 microamp. And the next one is 20 microamp. And the third current source is going to be a current source of 40 microamp. 40 microamp. And the next one is going to be 80 microamp. And if I do that 10 times, what is the last one going to be? 1000 times. That's going to be 1 milliamp. Isn't it? 1 milliamp. Okay? This was in micro. So that means that now I only need 10 of those. Now, 10 of those switches, my digital code, can simply control those 10 switches in series with the 10 current sources. So we don't need a lot of time to do that. Switching in one switch or a number of switches simultaneously in order to send that current to my 50 ohm resistor to the output. So that means that indeed my binary DAC can be real fast, because I only have to switch in one current source. I can do it all in parallel, real fast. But of course, if I do that, I have to answer the question first: how am I going to match a 10 milliamp? This was 10 milliamp, wasn't it? How am I going to match a current of 10 milliamp to 10 microamp? That's going to be real difficult. And very, very, very likely I'm going to have those glitches, because if I switch all of them out, the 9 bits before, just before the last bit is switched in, the sum of all those currents, which is 10 microamp below the 10 milliamp. So all the currents together is 9.99 milliamp. If I switch them all out and I switch in my 10 milliamp, am I sure that my 9.9 milliamp is indeed smaller than the 10 milliamp? If not, I get a huge glitch, because of the mismatch. So that means that speed is clearly the main advantage, but matching is a disadvantage here. Whereas if I take 1000, and here they are, I didn't have room enough to draw all 1000, my 1000 current sources I can match very well. It's just matching from one to the other, from one to the other. It's matching on a transistor level, as we just discussed. So matching is clearly the advantage. But the disadvantage of a unary one is, of course, I get a digital code coming in. It's not because with a 10-bit word 1011001110 that I can drive those current sources. I need to have a decoder that says that I'm going to drive, that converts my digital code in the thermometer code, that says how many of those current sources I have to switch in. So I need digital logic to drive all those current sources. So what is the difference between those two now? The binary one is the fastest. If your speed is your main interest, we are going to go binary. Full binary DACs do the left. Speed is perfectly, and the thing you have to check is, of course, static performance and glitches dynamic performance to see how well they behave, how you have solved your matching problem. The unary one is slower because we need logic to process my digital code into a thermometer code. It's going to take time, but matching is easier because now I have to match 1000 of those current sources. What is the result going to be? People can't make it in their mind. There are advantages there, there are advantages there. We're going to take a segmented DAC where the lowest one, where matching is not that critical, the least significant bits where the currents are still small, the least significant bits we will do it this way, and the most significant bit we are going to do this way. And now we have a segmented DAC, which is half 5-bit, 5-bit. Huge discussions whether you would go 5-bit binary and 5-bit unary, or you go 4-6, or you go 6-4. Huge discussions which one is best, but the segmented ones are the most common DACs, where part is binary and part is unary. Ladies and gentlemen, this is a good time to have a break. Let's have a break, and then we continue in 20 minutes. Okay, coffee is over there, plus water, and we'll start again 20 minutes from now. So, ladies and gentlemen, let's continue constructing such a DAC. I have mentioned already advantages, disadvantages. The biggest disadvantage is it's difficult to match a large current with the resolution needed depending on the number of bits. And on the other side, the main advantage here is the matching is okay, but the speed is going to be a problem because we need a encoder to convert my digital code into thermometer code. So actually most of them are segmented, where the least significant bits are binary and the most significant bits are unary. So when we construct such a DAC, how is that going to look like? Well, of course we need to have, you see here the binary. This is taken now for a 14-bit segmented DAC. 14-bit, if this is 6, this should be 8. So 2 to the 8, 256. We need 256 current sources here for the binary one, and 6 more. 6 more which are binary scaled. Those are all the current sources here. Those are simply derived as current mirrors, as you can see. So that means that we will have either many of those or binary scaled ones. On top of that, we need a cascode. Why do we need a cascode? Because that little capacitance here, which is going to be variable, that little capacitance is going to represent a different impedance, and a different impedance is going to generate a different current because we have a smaller resistor over there. I'll talk about that a little bit later. So that's why there is always a cascode, to make sure that there is a small output capacitance which represents a large output impedance. So there is always a cascode in there. And then this is not a differential pair, those are the switches. To switch in the current, to switch it away or switch it in towards the output. So those are switches, so they are driven by large voltages. It's a overdriven differential pair. And the whole question is there, well, of course, normally we have a latch in order to remember and to have the exact timing and to do the conversion of parallel to series to parallel, for example. So we need a latch which drives this one on and this one's off, but this has to be very symmetrical, because when you drive a, shall I call that the ECL gate in bipolar before, when I drive a pair like this, it's very difficult to drive those two transistors in on off without changing this voltage here, and that's the problem. Because if I switch that on and that one off, or vice versa, if this is a little bit earlier than the other one, I have a spike on here. And if this voltage changes, even with a cascode in there, this current is going to change. And we have worked so hard to have a perfectly matched set of current sources over there. So now the switches here, we must make them very symmetrical. And when we switch them symmetrical later on in the last realization, we have another switch over here. So another cascode over there to make sure that indeed we have a sufficient number of cascodes to have a very large output impedance and to make sure that the voltage does not change if the switches are switching in and out. So in this realization, we only have a cascode there, and we count on the fact that we have symmetrical drives for the two switches. And that's half of the papers of the DACs. How to do symmetrical drives. How to do symmetrical driving of the two switches. Another half of the papers is talking about how to get a high output impedance so that indeed that this voltage is not changing, and the voltage change is not going to give a change in current, giving you second, or depending on how you do it, third order distortion. Okay? So those are the two difficulties. The whole problem is actually first of all to make a set of matched current sources. Second problem is, how can I switch them such that this voltage is not changing? And the third problem is going to be, how can I make sure that the output impedance looking into this is infinite compared to this resistance, otherwise I get distortion. And those are the three problems of a DAC. And you will see many different kinds of solutions. How to keep this point stable? Well, how about putting an amplifier there and change the way you drive the two switches? Sounds complicated, but it's done. How about putting more cascodes than just one? 2 cascodes, for example. But you see already this is not going to help because it's the output capacitance, at least at high frequencies. It is the output capacitance that's going to make a difference. So can't we do anything there? So those are going to be all the difference between all those DACs. Few differences in terms of segmentations. 6/8 is a typical for 18-bit. Most 12-bit take 6/6, for example. When it's 10-bit, it's 5/5 or 6/4. It's very hard to prove that one is better than the other. The layout discipline is more important than the actual segmentation. But I'll show you some examples. First of all, the thermometer code. What does that mean, thermometer code? To make sure that you understand, well, you see here binary code going from 0 to 7, so this is 3-bit to show. You see that indeed if we go from 0, 1, 2, 3, 4, 5, you see that indeed the crossover from 1, 1 to 1, 0, 0, 0, that's where you have the summation of a number of currents, and here one larger current, that's where you could have a glitch. Not on a 3-bit level, of course. On 10-bit level, if you have, for example, 9 ones, and you go to 1, the MSB goes to 1, then you cross over from 0.99% of that current to 100% of the current. You could have a glitch there. This is binary, you see. And you simply drive with those digital words, you drive the switches directly, high speed. Whereas in here, you see immediately that in order to have 1, 1, then of course we need to have 3 current sources. For this one, we need 4 current sources. Here we need 5 current sources. Well, you see that we have to convert the binary code into a thermometer code. Because how do you drive with just one most significant bit? We need to have 1, 2, 3, 4, 5 unary current sources switched in, positioned at different points in space. So we need that converter, and that takes time. But at least monotonicity is guaranteed, and that's the advantage of unary code. So here again, in terms of mismatching, you see that indeed matching a large current with respect to a smaller one is a big problem. In a fully binary high-speed DAC, that's going to be the biggest problem, because then we have the matching on one single current sources, but it's much worse, because how do you match 10 milliamp down to a resolution of 10 microamp in a binary DAC? So in terms of mismatch, the mismatch is going to be much larger than the mismatch on a unary current. In a unary DAC, it's simply the mismatch of one current source by itself. All the currents are equal, so it's easy to match them. 10 microamp to 10 microamp, for example. Here it's 10 milliamp to 10 microamp, and that's much harder to do. In a segmented DAC, you're halfway somewhere. If it's a 5-5 segmentation, this is going to be 10 to the 5th. So it's going to be worse than in a unary DAC, but it's going to be better than a full binary DAC, of course. So it alleviates the problem a little bit. Should I go through the other ones? I think we have discussed all of them. This one is certainly, speed is not even in there. Speed should be on this side. Speed is an advantage here. Maybe we should add speed in there. Whereas matching is an advantage here, which is expressed by this. So same thing here. Binary is going to have a problem with matching. This is the same way to say that, for example, for 10-bit, in a fully unary DAC, it's going to be a lot easier to carry out a matching than in a binary one. That's why we take a bit of both. So now how do we do that? Well, for example, this is a circuit doing that already, where you see that indeed the most significant bits are actually current sources, which are switched in. And the least significant bits is binary with the R2R DAC. You see the R2R DAC, just a 4-bit resistive DAC, working on the last current which is part of the most significant bits. So this is a unary DAC, and this is a binary DAC combined. So actually it's a segmented DAC, twice 3-bit. This is the input for the reference, and here is the output. We simply collect all the currents in that resistor. It's not a high-speed one, of course, because there is an op-amp in there. But it's one way how this could be implemented. I'll show you other ways, of course. A simple one, only 6-bit. Yeah, the coding, I'm not going to say too much about it. This is all digital, of course. Those are the cascodes, remember. I'm going to give you values of cascodes in just a moment, and those are the current sources. And those are the switches. Okay. So how they are laid out. Of course, you have to make sure that those are going to be laid out in the same philosophy as we have discussed just before. And I'll say more about that in just a moment. Now, the other thing we have to have is a very high output resistance. Why is that? Well, if you have a resistance here, and this point goes up and down, depending on the switching, or as a result that this cascode is not sufficient, because don't forget that we have all different currents in here. That means that indeed we have different impedances looking into this. That means that even scaled up, the impedance looking into this is going to be multiplied by the gain of that transistor at this point here. We see that we have a division of that resistor with respect to the large output resistor here. So the question is to avoid, and that depends on the current which is flowing. We have small currents, you have large currents. That depends, we have distortion as the result of the finite value of this resistance with respect to this one. We can't make this 0, and we can't make this infinity. So there is always going to be distortion. It's got to be less than the least significant bit. So that means that what is the minimum distortion? What is the minimum output impedance we need for a 50 ohm, for example? Well, this can be calculated. Actually, this is the INL voltage, okay, where we have the number of bits, references from the Bos, the references in there. This is the 50 ohm. This is the impedance we are looking at. This is the unit current of the unitary current, 10 microamp, for example. And this is again the RL. This is the 50 ohm. That means that this voltage must be small enough. Well, for 10-bit, we need an output impedance of 6.4 megohm. And for 12-bit, look at those numbers. For 12-bit, because this is actually the same, this is very close, or nearly the same, for in parallel to 50 ohms, you see the same ingredients there. The distortion determines the spurious free dynamic range. It's a second order distortion. All currents are collected to one resistance. You see that for 12-bit we need to have something like 100 megohm. How do you do that? That's easy at low frequencies. At high frequencies, that's just a capacitance. So at low frequencies, I'll show you results where indeed, if I put, how many cascodes can you put in series? Depends on the supply voltage, of course. So at low frequencies, you just put another cascode in there. Okay. Then you have 3 transistors in series. This is the current source, all the current sources, a small transistor here and a small transistor there. And then I can have a very large output impedance, and then indeed the influence of that voltage here towards this point is 0, or the change of voltage on the current source, the VDS change is 0. And as a result, you have a very high spurious free dynamic range. At low frequencies. At high frequencies, it does not make any difference whether you add another transistor. You always have the drain bulk capacitance at the end. Even for a minimum sized, a minimum area transistor, you have a small capacitance here. So what can you do about that? That's the problem. So this simply says, well, 6.4 megohm, let's try to get this. Let's try to realize that. And the other problem is, of course, the matching. Because now if you put all those transistors here for matching, what can you do to exploit knowledge about gradients? Well, all of them use 4 squares with matching within each square. But each square can have a gradient which is like this. This is a bit simplified, there is no peak there, or a gradient like that. A gradient like that is, for example, an oxide thickness changing from one end to the other, or a K prime which is changing from one end to the other, whereas this is actually caused by a concentric problem, a symmetrical problem like stress, for example. If you put a chip, if you bond a chip, a square chip full of capacitances in a package, and there is some problem, depending on how it's glued or how it's bonded and so on and so on, you can have iso stress lines which are concentric. You can also have isotherm lines which are concentric. So there are several possible gradients. Not all gradients are changing from one end to the other. Gradients can also go like this. And then the question is, if I have a whole square, of devices, current sources to be laid out, how should I do that? If I take only one, it's clear I take the one in the middle. And if I take 2 in parallel, I'm going to take one over there and one over there. And if I take 4, and if I take 8 and so on, how do I do this? Well, you see that indeed, if I take 16, for example, a sequential scheme could be that you go and this is shown in one direction only, because then this has to be done in two directions, of course. We work in two dimensions. Huh? If you go from left to right, clearly this is no good. Huh? If I'm going to match this transistor to the next ones, for example, they are all on the same side of the same gradient. This is wrong. Huh? Also here. So this is no good sequential. Now, if I start in the middle, the second one, where I take one in the middle, and I take the other one over there, and then 3 and 4 on both sides, and then of course 5 and 6 and 7 and 8 like this. This is the conventional symmetrical scheme, but the problem is, this is fine for this one here, because if I take one over there and I take one over there, well, the negative and the positive deviation cancel. So that's good. But this is no good for this, of course, because if there is a symmetrical gradient, then, and I take them in the middle, then of course they are all on the same end. So it's better that if there is a symmetrical gradient, to be here somewhere, to start there somewhere, and combine those with those. And those are the A and B hierarchical symmetrical scheme. Those are this one and this one. And also there is a difference. Now we are simply talking about layout, where to put all my transistors. Huh? When you have 250 current sources, where do I put them? Well, if I put them here, for example, you see there, then clearly we have already a cancellation also from the symmetrical gradient there and there, because now one there, and then the 2 and the 3 and the 4. But there are still two possibilities. I can put 1 and the next one over there, and then 3 and 4. So you have to try out different locations in view of a linear gradient and a symmetrical gradient. Well, the errors are as a result of those 4 schemes are shown here. And A is the green one. This one is the green one. Green corresponds to a green light. That means that this is good. That's going to be the one we are going to choose, because indeed, when you look at the deviations and you go to 16 in this simple model, this is 0, huh? And on the other one, for a symmetrical gradient, this is 0, huh? Be careful, the 0 is not always on the same place. You see that indeed for the green one, the B one has too much deviation here in the middle, but the green one has a deviation which is, or an error which is relatively small, 0.24, 1/4 INL, whereas also here it's reasonable. You don't have big excursions as there. And that's why in this realization, it's the current sources are laid out according to scheme A. So this is something to watch. This is all about layout. Yeah. Another thing is, of course, well, what kind of error on one current source can I allow? Do I need an error of 0.5%, 0.25%? What is the kind of matching I need on the level of one current source with respect to the other ones? This is the sigma on the current. Do I need 0.1%? For example, if I go to 1000 corresponding to 10-bit, 1000, 1 over 1000 is 0.1%. Do I need to match all those transistors within 0.1%? No. We need some kind of an effective or RMS value or something, isn't it? It's not 1 by 1. It's 1 with respect to the neighbor and the other one and the other one, and then all of them together. So we can, this is a result of Monte Carlo simulation. And this ought to manage to put a mathematical expression through this. The unfortunate thing is the mathematical expression is a bit complicated. So it's much easier to remember a number than to go through the equations here. You see that indeed the mismatch that I need is that C, and this is mathematics, a funny function, and then depends on the number of bits, of course. And the easy number to remember is that if you would like to have a yield for 99.7%, then you would need something like 0.5% for 10-bit. And that's an easy number to remember. So if you need for a certain yield, there is an n which goes into that function that gives you a c and so on. You're welcome to read that paper to figure out what is that mathematical function. Your hobby may be mathematics, and then of course you like that. But the main thing to remember is that to have a certain yield, of course, we must have a certain amount of matching between those current sources. And for a high yield, here it is. This is the plot of all those values for different bits. For 10-bit, clearly you want to go to a yield of something like, you're not happy with 50%. Huh? I guess we are not. 99.7%. And then you see that those current sources must be matched to something like 2, 3, 4, 5, 0.5%. This is the number to remember, huh? For 10-bit at least. Okay. And of course, if you're interested in 12-bit, it's got to be a bit more tight. Huh? For 12-bit, here we go. Then we are at something like, this is 1%, and this 0.543, this is 0.25%, of course. Okay. So each time you go up a bit, you need more current sources. If you go from 10-bit to 11-bit, you need more current sources, twice as many current sources. But of course, each of the current sources must be better matched as well. So not only have more current sources, but they get bigger too. So that's why per bit, the size of any array, whether it's currents or capacitances, is times 4. Once for the number of current sources, and once because of the areas of the transistors which provide the matching in order to be able to get the same resolution. So for example, 10-bit and a reasonable yield 0.5%, 0.5% is not that difficult. This is far away from the 0.1% that you may think that 10-bit asks. Huh? So 0.5%. Of course, it's not 100% yield. 99.7 is good enough. So now, how does that lead us to? Well, here is that same expression as before, remember? Where I said there are two expressions we have to remember. The current of a transistor, of course, because we are talking about current sources all the time. And if you would like to match currents in transistors, I gave you that expression before. Depending on that matching of the WL, the 2% micron, and the matching of transistor which improves but doesn't go lower than 2 millivolt micron. 2 millivolt micron. Well, if you have knowledge of those two and you take a large VGS minus VT, depending on your supply voltage, probably getting rid of this, hard to say, then clearly as a result of the required matching on the currents of two transistors, I can squeeze out the area. And now area, that's half of my story. And the other half of the story is of course the current itself of the least significant bit. For example, for a 5 microamp least significant bit current, the smallest current, this will be, you will see values like 10 microamp, 20 microamp, 50 microamp. But don't forget for 10 bit, 50 microamp gives you 50 milliamp as most significant bit current. So be careful if you don't go too high. So 5 microamp in this case, well, it's easy to solve those two equations. Once you know what technology you're talking about, here it is, 2% micron, still use. And this one depends a bit on technology. For 0.35 divided by 50 is 7 nanometer oxide thickness, corresponds to 7 millivolt micron. For the AVT, goes in there, you take 1 volt, depending on supply, and there we go. That gives you the size of your unary current. Okay? It's a large channel length normally. Sure. That's static. Dynamic, much more complicated. There are 4 things we have to observe, and which I'm going to go back to each time I talk about a different realization. I have quite a few realizations in here, yes. First of all, of course, timing error, because if this is switched on before the other one is switched on, we're talking about how do you switch those two switches, how do you drive those switches, synchronization of those two. So many papers talking about how to drive two switches. It looks like we reinvent ECL, but in MOS, huh? To make sure that this point is not changing. Okay, and of course, well, if on the unary side you have a thermometer coder, then of course you have to delay the drives on the binary side a little bit. So we need a bit of logic to make sure that they all switched at the same time. Huh? Otherwise, that's how you generate glitches. Huh? So there is a lot about how to make clock and output trees to synchronization. Clock feed through, because we use clocks. Huh? Oops, clock feed through. We have some capacitance here. CGD, remember? It's small, huh? Fraction of a femtofarad. It's small. But if I switch this, if I have a step waveform here, that's going to come out here. and of course also on the other side, here. And that ends up on the output, can be filtered out. So this may not be that bad, it all depends how much it is. Voltage variation, this is the biggest problem at the drain of the current source, here. If this goes up and down, I have a signal here, for example. This signal over there, or that voltage over there, because you drive a current in here, is going to change the voltage here and a little bit over here. This change the voltage here and a little bit over there. If this changes a very little bit, that's why I've shown you that a VDS gives you a different current. And we are talking minute, very small quantities. So voltage variation at the drain of the current source transistors. That's where we talked about output impedance. That's what this is all about. But output impedance at high frequency, and it's repeated over here. Output impedance at high frequency, very similar. So those are the 4 things we have to watch to make a high-speed DAC. Let's have a look at some realizations. Here is number 1, 5.5, segmented from the same author as all the slides before. Done some time ago, nearly 10 years. Could say, well, this is old. Well, let's wait and see for the figure of merit. Moment of truth is always a figure of merit in analog design. Some kinds of circuit don't have figures of merit yet, like class AB amplifiers, band gap references. So we need some creative people to figure out figures of merit for some other classes of analog circuits. This one repeats everything I've said. There is nothing there. 5.5. You see when you go to the MSBs here, we need a thermometer decoder, and then of course all the switches, and here are all the current sources. Here we need a dummy decoder to delay things a little bit until this guy is ready to send the information over there. Switching matrix again, clock controlling everything. Switching matrix is of course giving rise to drive signals for the 2 switches here. Those are all the cascodes, and those are all the current source transistors, and that's it. How well does that work? Well, here are the results for example, 0.35. The beauty of 0.35 is that your supply voltage is still large, 3.3 volt, and as a result, you can have a beautiful cascode there. And look at the VGS minus VT, 1 volt. Wow. So when you go to, for example, 65 nanometer, it's terribly hard to make a DAC, because you don't have your VGS minus VT anymore. Okay? So you have to do calibration or something else. AVT used in there, the actual AVT, the A beta, it's close to the 2%, you see. This is a bit higher than what I would expect. You would expect 7, it's 9, it's a bit higher, I don't know why. We need 0.5%, remember the 99.7% 10-bit requires 0.5% matching on the current sources. The full current is 20 milliamps, so the unit current is 20 microamp. 20 microamp is the current in one current source. And with the 20 microamp, what are the sizes of the transistors? Well, here they are, 2 by 8. 2 by 8 is a current source transistor, current source. You see that? Current source. This is the switch, and this is the cascode. CAS is the cascode. And you see that those are going to be, this is the current source, it's going to be put in parallel with many current sources, but the switch are kind of small. Why are they small? To have small capacitances. Okay? And look at the cascode. It's the smallest possible device you can make in 0.35. This could have been a bit smaller, but it's just about there. This is only to have a small output capacitance, because that's going to kill the dynamic performance, you see? So it's all there. Now, how do I get that high output impedance? Study again. 6.4 megohm, how do you get this? So many papers explaining with all possible femtofarad capacitances everywhere. Not only around the switches, because don't forget each transistor has 3 capacitances. Also this one and also this one, but the most important ones are the capacitance at the output of the current sources, and this one tends to be very big if I put many current sources in parallel. And then comes a small one here. So this is going to be real small, it has a small capacitance. Well, how does the output impedance look like seeing over there? From the output resistance, which for high frequencies is going to be 50 ohm. How is that going to look like with all those capacitances? Beautiful exercise and body diagrams. If you're looking for one, here is an attempt to show you how this looks like. At low frequency, of course, we have indeed the output resistance and another output resistance. So we have RO, GM, RO, which is huge. And I can make it even larger and so on and so on. You could even try to put gain boosting around this one so you get even more. Okay, but that's not the point how far you go at low frequencies. You can go as you want. My problem is that at the higher frequencies over here, I'm talking 1 gigasample per second. I'm talking about 500 megahertz here. This is going to be capacitive, of course, and it's going to depend. It's going to depend on C1. It's a bit small, but it's a very small capacitors too. C1, which is over there. Okay. So that means that indeed this capacitance must be giving you something like 6 megohm. And if you calculate that 500 megahertz 6 megohm, you need somewhere a femtofarad. Okay. That's what we are talking about. Here we go. You need something like, it is C1, you need half a femtofarad. Half a femtofarad. What does that mean? That means that your width must be 0.25 micron in whatever technology. 0.25, and then you get half a femtofarad. And of course, no metal lines and all that all close together. Okay? That's what we're talking about. So this doesn't matter. It's all about this. And I'll show you several more realizations, all working on that high output impedance, this point here. Okay? Driving the two input devices. How do you actually do that? Symmetry and timing. This is a way to drive the two switches. Here is one switch and here is the other switch. And you see that indeed they're coming from here. And this is kind of a, shall I call that a gate, a CMOS inverter, the output of a CMOS inverter, and a latch. So this is a latch taking the digital input from the dummy decoder or from the encoder itself. And at the time of the clock it's applied to this latch circuit. But the problem is a latch is a digital thing. How can you control the actual voltage levels such that there is no voltage here? No solution there. You keep on seeing papers talking about this. How do you convert a digital signal into an analog drive for two switches such that there is nothing there? That's the problem. I will show you some realizations. Because if you just take a digital circuit here which goes to 0, 1, 1 supply, 0 supply, 0 supply, well, I can't guarantee that if you do that to those two transistors, you'll have a big bump on there, of course. So you have to have a circuit which actually carries out a digital function. Those are switches, okay? But somehow have an analog average value so that this point does not change in time. That's the beauty of the drive of the two switches of a DAC. If you have a solution there, you ought to make it. I'll show you what people have tried. This is a possible solution, but this is digital. But you see some more transistors in there to try to have a little bit of level shifting analog. So the average value of the drive voltage is about right. It should be perfectly right. That's an attempt. This one has that scheme with the num A with two dummy rings in there. You see it's 4 times the same, but mirrored. So we have 4 times that story of the selection of the current sources in there. With 2 dummy rows, it didn't work with 1 dummy row. The problem is you only know that 4 months later, of course, that 1 dummy row was not good enough for the matching. Okay, that's the problem with layout, of course. And here it is. That's the first time I have explained all about the matching and the drive for it. It works on a high voltage, and that's why it works well with the large features minus VT. But you see that if this is done at 1 gigasample per second, the maximum frequency is 500 megahertz. At 500 megahertz, 61 dB is not bad at those frequencies. How bad that is impossible to say. We need a figure of merit. I'm not going to ask you to remember all these numbers. No. But I'll put them together in a figure of merit. 2 times. An older one and a newer one. Okay? We have 2. Size will come in there too, although this is not that important. But it says that if you make all your capacitors or your transistors much bigger, you have better matching. So size comes in because actually it says something about the sizes of the unitary current transistors. Okay? So size will come in. Now also spurious free dynamic range. You see that indeed that the ratio is close to 60 dB or something. And figure of merit, this is the old one. I'll show you the new one later on. The new one has been proposed by a paper in ISCCC 2 years ago, and is slowly being used more and more. Okay, this is the older one. All figures of merit in analog design have speed and resolution or accuracy or signal to noise or signal to noise and distortion ratio. So speed, accuracy, and power. The speed is here. It says how far you can go with your signal, such that the spurious free dynamic range has gone down by 6 dB. By 6. And this is the resolution, how many bits? Okay. And this is the power you need for all this. What is the dimension of this? Well, this is frequency and watts. This is number of levels, 1000 or something. So this is frequency and watts. And you know, frequency and watts, rather than what most people still use, megahertz per milliwatt. The inverse is joule. Everybody talks for ADCs about joule and picojoule, but not yet for DACs. It's time we do that. And it's inverse joule. So it's time we convert that. Okay. So this is a megahertz per milliwatts, the inverse of nanojoule, the inverse of nanojoule, okay? This corresponds to 1 nanojoule, this is a tenth of a nanojoule, this is, and so on. And here is actually area. And of course, where do we want to be? We want to be in that direction, and we want to be in that direction. So we would like to be in that corner. And there you see that indeed many attempts before, Journal of Solid Circuit, Journal of Solid Circuit, CICC, AACD, ISCCC, and so on and so on. You see that indeed the 1 gigahertz one doesn't do the bad. The 1 gigasample per second doesn't do the badly. That was an ISCC nearly 10 years ago, but it's in that corner here. Okay. So that's one realization. Let's see what other people have done. When it's colder, I go faster. I have to keep my figure of merit constant. What have other people done? Let me take the most famous DACs. Yes, I went through all the most famous DACs. What does that mean? The ones with the best figure of merit. I collected them all, and at the end you have them all on the same slide. So what has this guy done? This guy says, I know how to make a DAC, and my problem is indeed, I don't know how to drive my switches. This is coming from the current sources, this is the cascode. Okay? And here are the 2 switches. And here says, well, the best way to keep this point constant here is to put an amplifier there, which has as a job to keep this point constant. Well, of course, that's a good idea. Shall we call that bootstrapping? Yes, bootstrapping, a bootstrapped common source node. This is the common source node of the 2 switches, and we're going to do bootstrapping. So if this has the tendency to go up and down, it gets additional current from there to make sure it's constant. Okay, that's what it does. And then, of course, it's going to pump additional current in there. Ooh. That means that we have to do calibration. So there is a separate conversion from the digital output to the analog SAR, which we have discussed before, to do calibration. And then, of course, at a low frequency end, this is going to be beautiful. At a high frequency end, this is hardly operational. So let's see what the result is. Well, at a low frequency end, you see that those numbers are beautiful. Yes. And of course, the capacitance here is going to kill it. You see the second order distortion is going to reduce it. And then what's left is the result, indeed, of capacitance on this little point here. But it's not too bad. Schofield did very well. Yeah. Bootstrapping the common source node works very well. Without the calibration, you couldn't get this, of course. But despite this pumping a large current, I recall the current was quite large, you get a high speed, not 1 gigasample, but at least half of that, and a lot of power. But to realize, to appreciate how much that is, we have to look at the figure of merit. Huh? So that's the bootstrapped common source node. The bootstrapped common source node. And it works quite well. That's another one, which is a 12-bit one, 7.5 instead of 6.6 segmentation. You can try to read it, a lot of talking about why this may be a little bit better. I've never seen proof of 6.6 versus 7.5 or 5.7. Working on fairly high frequency, depending on the power you pump in there, of course. Okay, all working on reasonably high voltages. Huh? Otherwise, you can't get your VGS minus VT. Remember, custom layout. What does that mean? Not done by some design automation system where you try to make by hand the layout of all the current sources, minimizing lengths and capacitances, and that's why this performs so well. The first one I was talking about, this one here was fully laid out by hand. A lot of work, of course. So that means that the time to design was excessive. Okay, and that's why you can go to such high frequency. If you do it by hand and you make sure all the capacitors are very small, you get to high frequency, of course. This is also done in the same way. And yes, it's not too bad. For 320 megasamples per second, Nyquist says 160 megahertz. Huh? 160 megahertz, 160 megahertz is here somewhere. Yes, here we go. 160 megahertz, 44 dB at 160 megahertz. Depending on the power that you consume, may be a good solution. But done by hand. Of course, this has to do with low frequency. That's a different story. We're looking at the high frequency end now. Okay. Another one. I'll show you the circuit in just a moment. Here it is. Keep an eye on this one because that's one of the better ones. Actually, analog devices. 0.18, but using a high voltage, and you know why. 6.8 now towards 14. And here again, how to make symmetrical the drive to the two switches. I'll show you another trick. So try to minimize the switching kick to the tail load of the current switch transistors. Yeah. Okay, and making the drivers as symmetrical as possible. Here it is. Here are the switches, double switches. So if there is kick by one, you switch the other ones out. Dummy switches, I would say, to try to keep that as constant as possible. That's one. Double switches, which was taken from another paper actually. And then, look at this. This is coming from the cascode. Here it is. And then the current sources, you know that story? Cascode. And this point here is an amplifier, taking as a reference where there is no switching, but equal devices. Take this as a reference and is going to try to make this point as constant as possible and adjusting the digital drive towards all the switches. Wow. So you're going to change the drive to the switches depending on the spike that is generated by the switches on this point. That's easier said than done, of course, because this amplifier goes to a controller. It's a lot of digital circuitry in there. It goes to the same decoder as before, but it works fairly well. It's one of the better ones. So you see how indeed that the common source point here is really the problem, and the switching is the problem. But since they are now included in the same feedback loop, you take care of both of them, if you can do that, of course. You can do that up to reasonable frequencies. Actually, you would expect 0.7 gigahertz coming out of this, but measurements are only shown to a fraction of that. I suspect all that digital stuff here and the driving cannot work at those very high frequencies. So it's used at a lower than Nyquist frequency corresponding to the clock frequency that is available. That's a bit suspicious, but the rest is fine. Another one doing this, a whole thesis on nothing else than how to drive all this. Yes? Yes, a whole thesis. You see the switches again? And how to drive those? You see the digital inputs? This is nothing else than the person says, I'm going to optimize my mixed digital analog circuit to make sure that there is no change here. Well, that's a nice example. You see some coupling there from left to right. Those are CMOS inverters. Those are also CMOS inverters. Shall I call that class AB drives? What an inverter actually is, a class AB drive. And what comes before is digital. This is just a digital inverter, I would say. A class AB amplifier plus local coupling. And the local coupling has its only purpose to make sure that you don't see anything there. Well, if you have other ideas about how to do that, why don't you try? 1.8 volt only, that's another difficulty. That's going to be a little bit harder to do, of course. That's a disadvantage. I don't know how much that is. We have to look at the figure of merit, isn't it? This got updated much more recently by people in MICAS, using more power but also higher speed. Look at this. If I take minus 6 dB here, I end up at 32, indicating that this is actually running at 4 gigasamples per second rather than 3 for which it was made. So you see that indeed optimizing the drive not to have any spike here and then go fully binary gives you the highest speeds. Huh? Many people today ask for real high speed DACs, 3, 4 gigasamples per second, but they would like to go to a higher number of bits. Huh? Well, maybe this is a starting point. Huh? You'll have to change other things. There is some glitches in there. I copied this to remind you that this is still one of the problems. The biggest problem when you go binary, and of course if it's only 6-bit, 6-bit is not that big a ratio. You can get away with this, huh? With 6-bit fully binary without having too many glitches. If you go to 8, you have a problem already. Okay? Meaning that indeed the glitch is small enough to be negligible with respect to the least significant bit current. Huh? So this comes in volt second. This is energy. Huh? Volt second is energy. So that means that indeed pseudo-segmented, what is pseudo about that? Maybe I should explain what is pseudo about that. Pseudo is a way in between where you don't really make a current which is so much bigger. The most significant bit is, for example, for 6-bit, this will be 64 times larger than the current of the unary bit. That means that rather than to make one big current, you just take those current sources as a parallel combination of unary currents. Why not? This is one of the rules of matching. Don't try to make a large current source. Just make a number of small current sources in parallel, and that's what's called pseudo. So the binary one is a number of unary one in parallel. And the difference is with the fully unary one is the layout. Because in the pseudo-segmented binary, you have the pseudo-segmented one, the currents are kept together locally, same space, whereas the unary one, the currents are spread out over a larger space. So pseudo-segmentation leads to higher frequencies, not high bits. There's nothing to do, this is just for high speed. Just for high speed. Let's go further. This is the guy who redefined the figure of merit. Yes. 13-bit. Whoops. This is no more just segmented. What's wrong? Well, the unary ones are split up again. 6-bit to get to 13. 6-bit, most significant. This is binary, 6-bit binary. And the unary one are split up in upper and lower unary. Because there is a difference in layout again to split it up. That's one thing, but the main thing at low frequencies is the calibration in there. So some redundancy is used in there. You see that indeed it's not just 3, it's 3 plus 1. And here it's actually 5 plus 1, but only 5 is used and only 3 is used. So redundancy is put in there in order to be able to do calibration. That's the main reason. And calibration is carried out on the currents in order to have 13-bit performance. Let's see how much is left of there. But the nice thing about this paper, unfortunately not in the Journal of Solid-State Circuits yet, maybe later, I don't know, is that indeed it explains what is actually the best way to characterize a DAC, even if the frequency is kind of moderate. After the numbers we have seen, 200 is less than the 320 and the 400 and the 500 and the 1000. Huh? But because of the calibration, we do get the 13-bit out of there, and it explains all this, how this is done. And indeed, when you see without the calibration, you only get something like this. With calibration, you get this. And this is all about small capacitors, as you can see. And at the highest frequency for 200 megahertz clock, let's have a look at the 100 megahertz. Half clock is 100 megahertz, isn't it? You get 55 dB. Is that any good? I don't know. We got already 61 at 500 megahertz, but the power was much larger. If the power is larger, of course you have to have better numbers. Huh? Okay? And area may be coming in there too. So keep this one in mind. Okay? So what else do we have? Maybe I should discuss this. Well, this is a guy who tries to get rid of the output capacitance. Beautiful. It's a bit darker maybe. I should have made it a bit clear. This is one of the last ones. Huh? ISSCC 2009, this is a year ago. Comparing number of high-speed DACs. Huh? Now what he's done, gee, we have 4 transistors here. What is this? Why do we have 4 transistors now? Well, this is the current source, okay? And this is the cascode. Yes, the cascode, one cascode. And this is the switch. And this is another cascode after the switch to make sure that the capacitance is not changing at the source, at the load here. So this is actually a cascode above the switch. So when the switches go on and off, that they don't generate spikes not only on the sources, but also at the drains. And that cascode has to be biased, of course. It's not sufficient to put a cascode in there. Cascode, by definition, is not a switch. What is the difference? A cascode has a DC current flowing in there, and here is the current source of the cascode. And that's the beauty. So that whole paper is about putting that switch in there with the current source. Putting a cascode with the current source. And what does that do? Well, if you switch on and off, here you see that the current source is no more there. The switch is off and the current source is off. Here the current source is on and the cascode is on and the switch is on. On, off. You see that indeed, when you look at that, you see that actually the capacitance on this point is not changing. It was the same before as after. So the real problem in those DACs is that the capacitance is changing between a switch which is off and a switch which is on. And because that cascode on top of the switch, he explains that as saying the difference between those two situations is that actually that cascode on top isolates the load from anything that's underneath from the point of view of small capacitances. And that's what matters. So when you switch on and off those current sources, it's the change of capacitance that matters, which is the same as saying the voltage across the capacitance which is there, or the capacitance value that changes. And indeed, that cascode, the capacitance of which does not change during the switching on and off of the current sources, since there is no capacitance there, you can go higher in frequency. Is that so? Well, look on the right. Look on the right, the highest speed ones are all put together, all the names, I have collected all the names in there, so you don't have to look where 6 is. It's the one we have seen, remember? The one where I have given you 2 slides on that. That's the one with the amplifier dumping current in the common source node. No, this is the one dumping current in the common source node. This was one measuring the voltage at the common source point and driving the switching arrangement to make it symmetrical. This was this one here. This is that early one, the 1 gigasample one. And the one with the cascode on top of the switches is this one here. This one here. Here we go. Well, first of all, you see at higher frequencies. First of all, it's hard to compare, huh? Because you don't scale the power consumption when you do this. When you just compare results, one could be 10 times the power consumption of another one. So this is only half of the story. But you do see that versus frequency, that old one here with the 1 gigasample per second didn't do too badly, huh? Of course, it only went to 500 megahertz. This one goes further, but this has about this work here at 2.5 gigasamples per second. Here it is. It's about 10 dB better, huh? At 500 megahertz. But yeah, it's an older technology. This is a newer technology, and the other ones are doing fine too. Sufferer is here. This is the one, and here is Schofield. Schofield was good at very, very low frequencies, but it stops already there. It was very comparable to the other ones. So all of those working on making that output capacitance smaller, or stabilizing that common source point, or trying to get rid of that output capacitance, all go in the same direction of high-speed DACs. This one has the advantage that it has a transformer output, so it has a larger output voltage than the other ones. But all the previous ones could have used the transformer too, of course. So this is kind of shifting the... And it was done in 65 nanometer, where it's not easy to go to a large VGS minus VT, using 2.5 volt in that portion. You're still looking for a real 1 volt DAC with similar performance, which I suspect is impossible to do, but that's up to you. So how do you compare all those? Well, two more before we do the compare. Let's do the comparison first, and then I'll go back to those. Switches, turn around the page. This is the old figure of merit, because you can't possibly remember all those realizations. You realize that. And this is the new one, done by Clara, because he says, well, what is this? This doesn't say anything about the low frequency performance, which is a very different setup. It's about cascodes, it's about your real matching. So we split that up in, we should say something about what happens at low frequency. This is at DC, but this means low frequency, of course. The spurious free dynamic range at low frequency. And it also says something about the high frequency end, half the clock speed, which is Nyquist. If it is there, it's not always there. And then we need the frequency in there, is just put the clock in there. That's easier, you always get the clock. And then on the side of the power, well, don't forget that a lot of the current that goes into a 50 ohm or something and takes power in the 50 ohm has nothing to do with the DAC. The power consumed in your output resistor has nothing to do with the DAC. The DAC itself is everything you do underneath, all those current sources and the switches and the logic to drive it and all that. So we should take out the power consumed in that 50 ohm, which is in here. For some of them, it makes a difference. For some other ones, it doesn't. But it does make a difference. And that ought to be our new figure of merit. A inclusion of spurious free dynamic range, both low and high frequency, and take out the power of the load. We all agree? Here we go then. And of course, the dimension is 1 over Joule. So at some point, somebody will have to turn that upside down, as they did for ADCs, and call that so many picojoule and nanojoule. Why not? But that's huge. I haven't seen it yet. So here it is. Just one example to make sure you understand what I'm doing, because each time I calculate the figure of merit, I have different numbers, because you do something wrong. So here is a numerical example, so you can do it right now. 200 megasamples per second, 13, you get 84 dB at low frequency, which is 12,855 levels. 55 at high frequency gets you this. 200 megahertz, 25 milliwatt, 1 volt peak to peak, in order to figure out how many watts are in the load, and this is not too bad here. But for some other ones, it makes a big difference. And this gives you the number, the FOM. And for the area of half a millimeter square, you get something like this, 2 to the n over area. And here it is. Beautiful slide. I copied this slide and I added some things. You see that this is that FOM 2. I should have added a 2 there. Please add a 2. But this is a very small, I hope. Even when it's cold, I'm sure you can add a 2. And those are the numbers, and here are 2 over area. And you see that indeed it makes a difference between all those current steering ones called intrinsic. But of course, if you do calibration, low frequency, high frequency, at low frequency benefits, it comes in there. Background, foreground. See that those 2 here are all the dark ones. And then the oversampling ones I didn't talk about yet. I have 2 slides on those. But when you look at that, you see that indeed the last one where I talked with the cascode on top of the switch, very high performance ISSC 1 year ago, doesn't give you all that much performance now. Because the power consumption, there is a lot in the load, but in the DAC itself, it doesn't do all that well. For example, this here, remember this one here? That one, this is this little triangle. I couldn't always put it in the middle, sorry. This is the one where he had that measurement of the common source point with the drive. That's this one here, does very well, one of the best ones. Wow. Also this one. Also this one, working on the drive makes a big difference, but this is a bit smaller than this one. It's a different technology, of course. This one, the 1 gigasample per second, is over there, which is not bad at all. This is all okay. Of course, if you start doing calibration, this area is easily beaten by doing calibration. Here it is. And more calibration, but not so good. I didn't even show you that when I've shown you this one, when I said something about it. And then, of course, doing more calibration. Here we go. Doing even better. Remember Schofield? Where there was a bootstrapping of the common source node plus calibration. And then, of course, you go to those values. But on top of the line, the highest figure of merit for the smallest dimension are the oversampling ones. Very recent. ISC 2008, ISC 2010, a few weeks ago. The oversampling ones. And this is why I have kept 2 slides in there. Not to say too much about it. Oversampling means that you have a... Here they are. Number 1 and number 2. Here they are, where you have a oversampling ratio again. High frequency clock. Quite often oversampling the signal that comes in. Oversampling, once you do that, of course, you can use the same thing with oversampling as was done before. You'll have to do dynamic element matching in order to have a large number of little capacitances. We need several DACs in parallel to get a high speed. Okay, I'm not going to say too much about those. And then when you look at that performance, all that is digital, meaning that indeed it can be made at a very small area for the performance that you get in there. This doesn't look to be that small, but when you compare with the performance of the other ones for that size, it's beautiful. And look at the power consumption, 1.1 watt. And this is one, and the second one is this one here. Very, very similar. Same application, only 24 kilohertz. Don't expect 200 megahertz when we talk about oversampling. Sure. Oversampling ratio 64. We have already a high-speed clock. I'm sure this will go up in frequency and time later on. But this is clearly for audio applications, where you would like to have a very high-frequency bit stream. Remember the previous one was 24-bit. This is also 24-bit. Also in 2 different paths, where you have to use the same tricks as in a oversampling A to D converter. 2 different channels with filters, of course, to get rid of the higher frequency, putting them together in a differential way in 45 nanometer CMOS. Wow. This is the most recent one. Look at the power consumption to get the same frequency. It's only half a milliwatt. And 0.05 millimeter square. This is the one that made it over there. So this is the one to be studied. Oversampling a D2A converter for low frequency because you use oversampling, leading to very small area and yet very high performance. And this, ladies and gentlemen, was what I wanted to explain to you in terms of DACs. And I hope you are all grown enthusiastic to have a better symmetrical drive and better matching and possibly oversampling DACs. Thank you for your attention.